I would like to now get into what are called lens aberrations. So I talked about a simple lens and how it works in an ideal setting, and that may be familiar to a lot of you already, but there are a lot of problems with lenses, especially as we increase the field of view. So if you have a very large lens, or let's say if you want the image produced by the lens to be very large, the focal plane to be large, let's say, then there are a lot of imperfections and a lot of problems that arise. And in virtual reality, we're highly motivated to do that, right? If you take a virtual reality head mounted display and you put a screen up very close and you put a lens in front of your eyes and you'd like to look through the lens at in different directions, you'd like to have a very wide field of view, that means that these kind of peripheral effects of lens imperfections are going to become very important. So they're critical to the engineering of virtual reality systems, and that's why I want to go through step by step and talk about different kinds of aberrations, right? Aberration means what? It means something not right, something different from what we would like to have happen in an ideal setting. So professional optical engineers deal with aberrations of all sorts, right? That's their sort of daily bread and butter, let's say, right, of characterizing aberrations, trying to compensate for them, trying to keep the cost of the lens down in terms of materials and manufacturing. All sorts of issues come into this. I want to give you just an idea of this, of the kind of things that can happen. So I will talk about lens aberrations. So first one I will talk about is spherical aberration. So the cheapest surface to cut for lenses is spherical. However, it is not ideal for generating a perfect image in the image plane. What tends to happen is the following. So you have parallel rays of light coming in, and then they do not converge at a common focal point. So it tends to spread out. So that means that there's no place where I could, suppose I wanted to place my projection screen here and I try moving it back and forth, some kind of vertical screen, I move it back and forth here. There's no place where I could put the screen so that I would have everything perfectly in focus. If I just use the central part of the lens, then it would be good enough. But if I really insist on using all of the lens and we get all the way out to the exterior, and that lens perhaps, you know, ultimately, like I said, it could be a big lens very close to your eye. If we insist on using these extremal parts of the lens, then the errors tend to get worse and worse. So that's one problem. There is a solution, so potential solution. You can make what are called aspheric lenses, right? If the sphere is a problem, use something else. So if you look for the word aspheric and lens, you can find all kinds of engineering literature and research literature on that. From what I've read, the ideal way to fix that is that for the lens, you make the incoming surface elliptical and the outgoing lens surface hyperbolic with very carefully chosen parameters, obviously. So that's harder to manufacture than a spherical lens, so it drives the costs up, but it may reduce spherical aberration significantly, and in an idealized setting it shouldn't eliminate it altogether. But spherical aberration is just one of many problems that a lens designer has to focus on. So let me give you another one. 2, optical distortion. In this case, when we have a high field of view, this might happen. If we put perfectly square grid lines, perfectly straight grid lines in front of the lens, and if you do this, for example, if you take the head mounted display from the lab and you can do this, you can take out the lens cup and put it over some graph paper, it will look something like this, right. So the straight lines become curved. This is a kind of distortion called pincushion distortion. And notice that if we were just going to use the lens in this central part here, it might be good enough and you might never notice. You know, this is a pretty extreme example, but you can see that the further you get away from the center, the stronger the divergence is between being straight and being curved. And since because people in modern virtual reality systems want the field of view to be as wide as possible, they have to deal with this problem. And it might not have been a problem maybe 10 or 15 years ago in some other kinds of systems where the field of view is very narrow, where it generally looks like you're just staring at a small screen. But if you want to have your entire field of view filled with the stimulus presented by the virtual reality system, you're going to have to deal with this kind of curvature. Another common case, which is essentially the opposite, is opposite or inverse, is called barrel distortion. The lens ideally is radially symmetric, right? So it has radial symmetry, and so these distortions tend to be radially symmetric as well. So then you can compensate for them by just making a kind of transformation that adjusts the radius in polar coordinates. So the theta part doesn't have any kind of transformation, but you just kind of perform from the center. If you want to compensate for this, you just perform some kind of radial stretching, and the amount of stretching you do does not depend on theta. That's generally how you would compensate for something like this. So these two are inverses, and what's actually done in software, so I will mention just a little bit. This is done in head-mounted displays, and I'll give a little more detail on this later on in the course. But in software, barrel distortion, and I think I called this T-dist when I just gave you it as an example when I did the chain of transformations. Barrel distortion is applied to compensate for the pincushion distortion of a head-mounted display lens. So it's you know, I like to think of it as a barrel pincushion annihilation, right? So the pincushion is one kind of distortion. You apply the opposite distortion, which is a kind of mathematical inverse, and then when you put the two together you get the identity, which hopefully should be everything is perfectly straight. It's easier said than done. It's very, very hard to tune the parameters of your barrel distortion in software so that it compensates perfectly. There are a couple of interesting reasons for that. Mainly the problem is that human perception is involved and the human optical system is involved and your eyes move. All of this together causes some great trouble in trying to fix this problem, which I'll give you more understanding of as we go on. Questions about this? All right, so one more. I have 5 aberrations I'm going to cover here, so it's kind of a depressing topic, right? It's just more, it's going to be a list of 5 things that interfere with the performance of these systems and degrade your virtual reality experience, especially if you demand having a high field of view, which I think is reasonable to demand. So another one is chromatic aberration. So in order to explain this, I should start talking about light waves and frequency decompositions of them. So remember that light, one way to look at it is composed of waves varying between about 400 nanometers and about 700 nanometers in wavelength. Right? So we gave the formula for converting between frequency and, you may remember, just a simple formula, F equals C over lambda. Frequency is the speed of light divided by the wavelength, so you can convert back and forth between these. Now you've seen the visible spectrum before, perhaps, right? We talk about the basic colors of the visible spectrum. Right, the colors red, orange, yellow, green, blue, indigo, right. So when people talk about the spectrum of colors, right, you've seen light shining through a prism before. I'll show examples like this in a bit. They're talking about pure sinusoids that correspond to one particular frequency or one particular wavelength, right. So that's a very unusual situation to have. It may happen if you generate a light using a particular laser, for example. For light that's bouncing around in this room right now, there's many different wavelengths all propagating at the same time, right. So there's a whole mixture of those, and that's called the spectral power of the light that's propagating, right. So those of you with a signals and systems background should understand analysis of signals in the Fourier domain, and you can talk about the frequency components of that, right. So if you've done some Fourier analysis kinds of things before, this should not be surprising. It applies to light, it applies to sound, it applies to all sorts of problems where there are propagating waves. So that's something to consider, the spectral power of light. Again, in terms of the spectrum, I'll say it once again, when we talk about the visible spectrum and we pick a particular place along it, we're just talking about a single blip in terms of this overall spectral power of light. There's one place along the spectrum where there's light at a specific frequency or wavelength. There's not a mixture, but more generally there's a mixture. So spectral power of light, you could say that that's like a histogram, if you like to think that way. It's not necessarily discrete like this, but it may be helpful to think of it as in a continuous way, but you can think of it as kind of a histogram of wavelengths. And we're ultimately going to have light going into our eyes through the pupil and hitting the retina. So what is the spectral power or spectral distribution of that light? What does it look like, right? Are there more greens, more blues, some reds? You know, what exactly do we have as we look at the range of wavelengths? So there's two things that affect that. One is going to be the light that's emitted from sources, and the second thing is going to affect that is the various materials in the environment. How do they reflect the light? That's going to affect our perception of the color of something, right? This board appears to be green and white in some way. I think we all see it like that. That depends on the properties of the board and the properties of the lights that are shining on me now, which as I see them they are mostly white, and there's a good reason for that. So these are the two things. So I will write them as there's the emissions of the light source. So for example, maybe I write 400 here and I write 700 here. So these are in nanometers. So I want this to be the wavelengths. And then one example I'll draw. These are just rough plots, but they give you some kind of idea. based on reality in some way here. This plot could correspond to daylight. And this may correspond to an incandescent lamp. Right, so we consider the light source, and generally when we have a light source, if we're going to engineer one, if we want to do photography or videography, then we would like the light source to contain as much of the spectrum as possible in the visible range, and it's also best to have it close to equal, you know, so that it doesn't overly emphasize let's say red instead of green, right. So you'd like it to be what we call white light, which would be a perfect balance across the spectrum with the entire visible spectrum represented. When we get off to the extremes down here, maybe what's that called? Shorter wavelengths is what? Infrared. Wait a minute. Let's see. Lower frequency, longer wavelengths is infrared, right? So that's over here, I guess. Yeah, and again, we can always change using this F equals C over lambda formula. So I guess based on the way this is drawn, this is the infrared part, and incandescent bulbs they tend to get hot, right? They generate a lot of heat, which should generate a lot of infrared radiation, which is why it seems to be peaking here, would be my guess. So ultraviolet would be on the other side. All right. So that's one part, is the emission of the source, and then there's the spectral reflectance of the material. Now both of these subjects, emissions of the source and spectral reflectance, become very important in computer graphics. If you want to make a completely artificial scene, a kind of virtual scene, and you want to render how that might look, you need to make models of these things, right. We make artificial or virtual light sources, we will make virtual materials and then decide what its spectral reflectance property should be, and then hopefully it will look, or convince our brains that it looks reasonable, much like it would look in the real world. So even in computer graphics this is very important, but it's also going to be important just in our understanding of how human vision works in the real world, because it's part of this optical system. I'm going into all of this explanation because I need to explain chromatic aberration, but this is also going to be useful in many of the things we do in the course here. It's useful generally for virtual reality. So spectral reflectance will be another kind of plot. Maybe I have at the top of the plot 1 for total reflectance and 0 for no reflectance. So this is the amount of reflectance. Maybe I could call it the coefficient of reflectance if you like. So for example, up here, well, still let me write my so have my wavelengths here, and one example I'll put along here is snow. How's that, right? So snow generally looks very, very white. It pretty much reflects everything very nicely, right? But it is not a specular reflection, in that when I look at the snow it does not look like a mirror. It's a diffuse reflection, but it tends to not look like it's some special color, right? So that's because it has this kind of very ideal spectral reflectance, ideal in terms of looking perfectly white or just reflecting back whatever the light source is. If I shine a perfectly red light with only one wavelength in it on the snow, what color will the snow be? What's that? Green? Red. It'll be exactly the light that I shined on it, right? That's how it should look. Ideally, you know, there may be some distortions and things. If I take something else, like say I take a look at grass. Okay, I realize maybe this isn't the idealized color here for grass, but should show up a bit. May tend to peak somewhere, and it may peak right in the area where that wavelength should correspond to. Green if the grass is green. If the grass turns yellow because it's too dry, then I guess it'll move somewhere else, but it may have a more distinct signature if it's something we perceive to be a particular color, so that even when you shine white light on it, you may still get a very distinctive amount of emphasis along a particular part of this visible spectrum. So those are the things we perceive as having a particular color. You shine a white light on them and not everything is reflected back. It's very specific. The more specific it is, the more we perceive a particular pure color. Does that make sense? All right, so we have this spectrum now. So now think about it. There's some light sources, the light's been bouncing around, and it could have multiple interreflections off of different objects based on the spectral reflectance and how much power gets dissipated. Remember I said some of the light gets absorbed as well, so there's less and less as it goes along. Well, by the time it's all done, let's suppose now that light decides to hit a lens, right? So if the light hits a lens, then here we have parallel rays coming in, and let's do it here off at the extreme. You may have seen a picture like this for a prism before. So as the light comes in, it turns out that the speed of propagation of the waves through the medium depends on the frequency, right, or depends on the wavelength if you like, either way. Which one's going faster here? Red's going faster through it, and blue is tending to get more stuck. Is that right, or is it the other way around? Right, okay, so red seems to be going faster through here. If it were going straight through, then there would be essentially no effect, right? So the shorter the wavelengths, the slower it goes through the material for the way this picture is drawn. And so if that's the case, then you'll have a focal length for pure blue, you'll have a focal length for pure green, you'll have a focal length for pure red, and if you generally have some kind of distribution, some distribution that corresponds to the spectral power of light, or some histogram of various wavelengths, then the focal plane will really be distributed in some kind of way, right? You may want to put it in one place to really focus the reds well, and another place to focus the greens well. That doesn't sound very satisfying, right? But that's what you have to deal with. What are some potential solutions to that? So we're still under chromatic aberration. I've shown you a picture there of it. Possible solutions. So one, find a lens material, find and use a lens material with a high what's called Abbe number. What that means is that it's low dispersion. What that means is little dependency. Well, let's see. Let me put it this way. The refractive index n depends little on wavelength. So there are some materials that refract the same way. The speed of light through them does not vary much based on the frequency or wavelength. So that's one way. The trouble with that is that these materials tend to be very expensive. So in mass-produced consumer products, this is not very reasonable, unless someone finds some new material that's all of a sudden cheap, easy to manufacture, and all of a sudden saves us. Number two, form a compound lens with two materials. All right, two different materials or media. So this is commonly done in lens design. So there may be one material which is causing separation, the crown glass, and then another kind of glass called flint glass, which is put right up against the lens to try to bring them back together again. So you can use two materials, play some kind of tricks. It's a kind of delicate art for the design of the lens. So optical engineering becomes very difficult because of these. And again, if you can get the costs right and the materials correct, not too brittle, and whatever other things you need, the optical properties, you may be able to make a compound lens like this called an achromatic doublet. And you see even in this picture it doesn't show it being perfectly compensated, but it may greatly reduce the chromatic aberration. A third trick, which would be a computer science kind of solution, just fix it in software, right? And that is being done right now in current head mounted displays. So compensate, just as we talked about the optical distortion, the barrel distortion compensating for pincushion distortion, you can also compensate in software by shifting or distorting based on the, let's say, subpixel wavelengths. Don't quite want to put pixel there because if you hold a magnifying lens up to a screen, which I suggest you do, and then you can study the pixel structure very carefully, you'll see that what we call one pixel in computer graphics actually corresponds to several subpixel elements that are lighting up, right? They don't correspond perfectly. They're not just, it isn't such that R, G, and B are just all superimposed in one place. It's a kind of pattern, a tiling pattern. For example, the screens in the lab use a pentile display. You may observe. All right, questions about this? So I think that all of them have some kind of flaws. The software compensation is not perfect. These other solutions are costly and again not perfect. It's something that we unfortunately face. Yes?
So in the human eye, do we have this chromatic aberration, or is it because?
That's a wonderful question. Yeah. Yes, we do. So in the human eye, we have chromatic aberration, but your brain learns to compensate for it. So you don't see it. And this is one kind of theme that will happen over and over again. There are all kinds of problems that our eyes have that our brain is just fixing. The most interesting one, or most well-known one, probably being the blind spot that's due to the optic nerve. So that part of your retina is essentially missing. But do we see a blind spot? I can show you some experiments where you can try to find it, but it's interesting. But our brains are repairing all of these flaws. So that would be analogous to number 3 here. So the software can fix it. Your brain also fixes it. No, that's a very, very nice question. Sure. All right. So that was. Oh, so these 1, 2, and 3s are inside of the big number 3, which is the third aberration, which was chromatic aberration. So I probably should make these. Should have been little 1, 2s, and 3s in that sense. For the record here, those are just inside of my main numberings. So number 4 is astigmatism, which corresponds to elliptical eccentricity of the lens. I will just show a quick picture of this. So instead of having perfect radial symmetry, don't do that. Instead of having perfect radial symmetry, when you have light waves propagating in the horizontal plane going through the lens, there will be one focal point. But when you have light waves propagating in a vertical plane, there will be another focal point. And so this will mean that there's no place where you can get a perfectly focused two-dimensional image. Those of you in the audience who are wearing corrective eyewear, some of you may have an astigmatism, and that cannot be fixed by just changing the diopter, right? So any problems of nearsightedness, farsightedness, you can just play around with the diopter, do some adding and subtracting, and fix it however you like. And then in a head-mounted display, if it has adjustments, you could move the lens forward or backwards away from the screen to compensate for your nearsightedness or farsightedness. However, You cannot compensate by just moving lenses back and forth for astigmatism. You have to design some kind of corrective asymmetry into the lenses to fix this. So there's some examples you may have seen before where some letters may look sharp along one direction and then blurry along the other, or vice versa, and there's no way to, your brain may try to find an intermediate focal length, your eyes may try to find an intermediate focal length to try to bring everything roughly into focus. So astigmatism is the fourth one, and the fifth one is called coma, sometimes called chromatic aberration instead of chromatic aberration. I'll just call it coma. That's derived from the word comet because it appears as a kind of comet image here, and this tends to happen when the part of the image you care about is very far away from the optical axis. So this is the central optical axis here, and these rays are coming in at an angle. We're still looking at parallel rays for this, and so at the focal plane you get these kinds of patterns that emerge. This gets particularly worse for thicker lenses because the waves are getting offset and shifted as they travel through the lens, and you get this kind of repeating patterns. You might have, if you've ever played with a magnifying glass on the sun, you may have seen some kind of repeated patterns like this. You may also see it sometimes in photography or in movies. You may see some what appears to be a bright spot, but then a bunch of smaller bright spots trailing off from it. So that is an example of this coma pattern you get. It's an example of what's called an airy pattern, A-I-R-Y pattern. This will also happen in diffraction. So you may have seen very simple examples in physics classes where you form a slit in a material and then look at how the light diffracts as it goes through that, and the wavefronts will tangle in some kind of complicated interference pattern and it'll generate stripes. So that's the kind of thing that's going on here. That's an example of an airy pattern. This coma is an example of an airy pattern, and you will indeed see these kinds of things if there's a very bright, distinctive, say 1 pixel is lit up and it's over at the periphery. It may appear as some kind of comet pattern. So it's harder to find those, but I've seen it happen before. So that's all of the optical aberrations that I want to cover. Any questions about that?